Well, good evening, everyone. We're really pleased to be joined by Nick Hill this evening. Nick's recently retired from Historic England, where he was a project manager in the technical conservation team for over 30 years. Is that right, Nick?
Yeah, that's right.
Nick's been responsible for some of our largest rescue projects, including Apthorpe House in Northamptonshire, Jacobean Country House, and the J.W. Evans Silver Factory in Birmingham. Most recently, Nick has managed the project at Shrewsbury Flaxmill Maltings, which is the earliest cast iron frame building in the world, which is what he's here to talk to us about this evening. So if we can either put questions in the chat as we go along, or we'll do a bit of a question and answer session at the end. And I think we'll try and deal with the questions in the chat at that point too, if that's okay with everyone. Everybody's microphone is muted or should be muted at the moment, but we will open that up for questions at the end of Nick's talk. So I'll hand over to Nick. Thanks, Nick.
Okay, thanks very much then. I'll just start on the sharing. Hopefully this will work. Yeah, there we go. Okay, does that come through okay there, Kim and Rob? We're on the first slide, right, are we? Yeah, great.
Yeah.
Okay, well, thanks very much for inviting me to this. This slide is slightly out of date, as Kim's just said, because I'm now the ex-National Conservation Projects Manager for Historic England. I was there for 31 years, and the last 10 of those years was working on this project, which I was the project manager for Historic England. Working with a very much larger team altogether on this wonderful site. It's a large industrial site, just 1 mile northeast of a town centre of Shrewsbury in the West Midlands. And it's been a major Historic England rescue project from 2005. As you can see there in those slides, it's been a major transformation. Focus for this talk, it is a much larger site and there are very many different aspects to this, but the core building, the most important one really, the most interesting one is this centre one that we're looking at here, the main flax mill itself, which dates from 1797. And was at the centre of our £28 million regeneration project. Here you can see a wider view of the site as it was a bit around about the time Historic England, English Heritage, as we were then, took over in 2005, and this is the main mill. Just checking, can you see my mouse? Okay, moving around on the main mill building.
I can, Nick.
Yeah,
but
yeah,
Pat,
okay.
Pat's telling me that you can't see your screen share at the moment. So could anybody else confirm if you can see the screen share?
I can, Kim.
Yeah. Could, in the chat, maybe?
Sounds like it may be a localized problem then. Yeah. Okay.
Yeah, everybody can see it.
Yeah. Okay, that's great. Yeah. Okay. So yeah, large industrial site, as you can see there. The site extends all the way around the sort of main boundary up to the railway track across the line of a former canal that came through the middle here. All of this is now swept away, and you can see something of the transformation. Here's it, a recent aerial view with it moving on. So we're going to be looking in particular at the main flax mill building here, dating the main mill, dating from 1797, and focusing on that. Its claim to fame and the reason why really Historic England got so invested in this site is that it is the first iron frame building in the world, and it's that in talking to engineers as you are going to be focusing on that engineering aspect of the site and the project in particular this evening. There's an awful lot of different angles. It's a wonderful teaching resource in many ways, apart from anything else, this site, but we'll be looking especially at the engineering, which was really a very major part of this project. So this is on the 3rd floor of the main mill. You can see this wonderful columned iron frame here, which we'll be talking about. It was built as a flax mill in 1797, and initially was producing, in particular, flax. Making linen thread was its sort of major thing out of flax. There were 3 key people really in at the beginning of it. John Marshall, who was the owner of the flax mill business, the principal owner, along with some others from more locally, but he had a major flax business up in Leeds. He decided to build a new factory down in Shrewsbury because he had some other business connections there, but also in particular that down in that part of the Midlands at the time, they had particular expertise in ironworking. And especially had this chap, Charles Beige, who we don't actually have any image of, but we have some of his letters here, which is a key part of the history of the site. Charles Beige was a rather extraordinary fellow who was a man of many parts, really. His father had an iron rolling mill. He had an interest in iron structures from a very early age, but he was kind of strange things. He had a background as a land surveyor as well, wine merchant, but he went on to have a major career in iron and its design. He worked with Telford later on his career. But interestingly, he was very much a sort of designer and inventor, really. John Marshall, who was the ultimate businessman and the successful, great entrepreneurial spirit, really. He has this nice phrase where he said that Charles Beige had a talent and cultivated understanding, but was not a man of business. So there you go, different types, really. But this unsung hero, really, of it in many ways, I think, is the third chap there, whose bust you see there, William Hazeldine. He was the ironmaster, and it sort of fell to him, really, to be, he had a local foundry in Shrewsbury where the whole of this iron frame was made. And I think we often give Charles Beige, the designer, a major credit for it. I think he wouldn't have got past the starting gun, really, without the skills of William Hazeldine and being able to translate those dreams into reality. There's this wonderful quotation about William Hazeldine, and at the time this business of making things out of iron and hot metal being poured in a foundry was seen as rather magical. And somebody visiting his works at the time talked about him as being the arch conjurer himself, Merlin Hazeldine, and these ability he had to sort of make things out of hot metal. But Charles Beige, we have quite a lot of information about him because we have this set of his letters, one side of his letters, writing to William Strutt. There was a great race on, really, to make the first iron frame building in the world at the time. Ferment of ideas, particularly in the Midlands. And he was experimenting with different ways of doing things, writing to William Strutt, who was the sort of, who built the next iron frame building. And it's rather marvelous. These give you a real insight into what was going on at the time. And if we look in the middle of this letter, he's talking here about, he's realized that you have a sort of a coefficient of thermal expansion, and that, you know, if you build a building out of iron rather than timber and masonry and brick and so on, as they were used to, what happens if it expands? And he says, I think your pillars are near 50 feet long. By the above rule, a difference of 30 degrees should push the floor of the upper story 1.5 inches into an arch, supposing it level in the coldest weather. So he's sort of realizing that. But then the killer point really is there right at the end, where he says, in point of fact, does this happen? Question mark. They were at the leading edge of this stuff, and the only way they found out really was by experimenting and doing things, testing things to destruction. Unfortunately, it doesn't move around by 1.5 inches for whatever reason. Otherwise, it would be a complete disaster as a building. But there we go. You saw in the earlier slide there, just going back one, about this star-shaped columns, and these star-shaped columns feature quite heavily in the design of the main mill. He says, writing to Strutt, he says, we're differently advised about the strength of pillars. This shape, the cross shape, which he sketches out there, which nearly resembles yours, is doubtless the strongest. And of course, you know, as we know now, they were wrong. That was circular hollow section is the most economical use of metal. But there we go. That's what they thought. And certainly it was maybe easier to cast at this stage with the earlier casting methods. But when we're talking about the first iron frames, the race on was really not so much about just the sort of virtuosity of building in iron rather than any other material. What it was all about was making fireproof buildings. And that was because, particularly in big industrial buildings, and this is the famous flour mill, Albion Mill in London, which caught fire a few years before the main mill was built in 1797. There'd been a series of disastrous burnouts, and Marshalls, in fact, a company in Leeds, had had a major fire, destroyed one of their buildings just a year or so before the main mill was built in Shrewsbury. So that was what it was about, trying to build a building which didn't have timber, and therefore didn't suffer, they hoped, from this sort of catastrophic burnout. It wasn't really that they were worried too much about the people and the workforce maybe back in those days, but it really wiped them out in terms of all the expensive contents and machinery and the products which were destroyed. And in particular, the insurance was getting to be completely unaffordable because they'd had a series of these things. So this is our reconstruction of how the building would have first looked as built in the around about 1800, with this iron frame inside. It still had external walls of brickwork, and there's engine houses at both ends, as you can see there as well, and this rather extraordinary multi-pitch roof, which we'll be seeing a bit more of as we go through. One of the other parts of this is that it was built also to receive a steam engine. These are the wonderful original drawings for the steam engine installation by Bolton and Watt in the South Engine House at the Flaxmill 1797, which survive in Birmingham Library archives, and show that. It was one of the earlier ones, not the earliest in this case, but one of the earlier ones which were these mills not built with next to rivers by running water so that they could use water power. It was actually built independently next to a canal, and in future years next to a railway, so that it could be powered only by steam rather than by water. But I want now to particularly just look at the iron frame. Especially, it's a 5-story building. We talk about it as being the grandparent of the skyscraper, which is possibly bigging it up a bit, but it's a great strap line, a sort of sales pitch line for the project. And it is in a sense, although not a particularly tall building at all by modern standards, it is a first-story building. And the great innovation here, people have been using cast iron columns for some years beforehand. The innovation was that they were then using also cast iron beams. In the years just preceding this, people had been experimenting with sort of timber beams clad with iron plates and things like this, but this was the first one which actually had a full iron beam structure as well. And then the floors were made then with jack brick arches, as we'll be seeing, vaulted brickwork spanning between the cast iron beams, so that in effect you had then a completely timber-free building, which theoretically was then fireproof. This is just a nice reconstruction video which shows how the building was put together. It's one of the extraordinary things about the flax mill, as you get to know it over the years, is it's just an incredibly elegant structure. As you can see there, it's really quite slim. It seems quite chunky when you're sort of just on a single floor, but you see the whole thing set apart like this, and it is quite incredible. And this is the way they go together. Besides being, we think, well, we know the earliest iron frame building in the world, we think it's also one of the earliest that actually uses nuts and bolts in its main construction method, rather than just individual straps to trusses and ties and so on, but actually a bolted up structure in that way. But alongside that internal iron frame, there's the external brick walls, big solid load-bearing brickwork walls, and then of course the floors, which are then formed, as I said, out of vaulted brick arches. They've been then overlaid, as you see in this engineer's drawing, with later concrete screeds and so on. But that's the way it's then put together. So that sort of obviously adds a considerable amount to the way it performs structurally. And you can see there up at the top the way that the roof truss, there's no sort of proper truss action in the roof. It's thought that at this early stage with cast iron, beige and Hazeldine maybe didn't quite dare to do a complete free-spanning triangulated truss across this top span, as happened in the later buildings. By 1810, they were building those kind of structures. But here it's a sort of propped beam, central beam, just sort of a central column, beams propped on that, and then that gives you then this sort of multiple valley roof, sort of sawtooth roof, which is rather unusual kind of thing. So that's the Flaxmill reconstruction drawing. This is remarkably almost every detail on this drawing that we put together with some very talented people is based on hard evidence. Shows a giant chimney that had replaced those early Bolton and Watt steam engines. There was a massive engine house then that was built down here with big boiler houses and a huge chimney stack dominating the mill. All of that later to disappear, and a whole array of other things out here, including an early gas supply. So they had the whole gas lighting as well, and a whole complex of other buildings too. But moving on through the history of the building, the flax business with the Marshalls and Company lasted into the 1880s, but then flax and linen fell on rather harder times. There was a lot of competition coming from the cotton industry, which was flourishing at the time. And the mill then was closed down as a flax mill, had a few dormant years, and then rather remarkably, and the reason why it survives really today, it found a second reuse. We're often talking about with industrial buildings seeking to find a suitable beneficial use for keeping them going. And this use, the next use, was as a maltings, and was rather remarkable. It gave the building, saved the building. It really would have been demolished, site cleared, and something else built there instead. As you can see, what happened was that the windows, and this is very much part of the structural story, were then most of the windows, 2 out of every 3, were blocked up as part of that, because inside in the maltings period, what they wanted was a sort of, instead of that great light interior with the large windows flooding this sort of narrow floor plate and throwing light in onto the textile machinery on the inside so you could see what you were doing. For the maltings, what they wanted was a much darker floor with a sort of humid environment inside, just controlled by shutters rather than windows. And then these great floors, which had been full of textile machinery and all those processes, everything was stripped out and became these big empty floor plates where a floor maltings could be established, laying germinating barley across all of the floors as we go. So right, so that's the background then of the sort of 2 major periods. It's called the Flaxmill Maltings because each of those lasted for about 90 years. Sadly, the maltings itself then closed in 1987, and as an industrial building, it then really needed to find another and different use, which was quite elusive for some time. It was a great big building. It sat in a rather sort of less favoured part of Shrewsbury, somewhat outside the city centre, and surrounded by a sort of less well-off part of the town. There was a series of 3 developers who tried to make something of it, but each one of those was defeated by the sort of technical problems which they sort of consistently underestimated, and the extremely sort of complex and high cost that was facing them. So eventually, in 2005, after many other efforts and things had been tried, Historic England, English Heritage as we were then, stepped in as a guardian of last resort and bought it together with support from Shropshire Council and Advantage West Midlands, the development agency, and so on. So we became the proud owners of this derelict pile from 2005. We rapidly had to do a lot of survey work, investigation, see what was wrong with it. And one of the first things in 2007, this huge scaffolding went up, which was not just in the normal way to provide a scaffolding and a temporary roof to keep the water out, but as we'll see, was actually to hold the whole building together, which was in danger of bursting apart. And that's very much part of the engineering and repair story as we go on through the project. Historic England, being who we are, actually then commissioned quite a major series alongside all of the other technical survey, investigation, getting engineers, architects, and so on, invested in the project and finding out about the detail of all the defects. We also did a lot of historical work. So a book was actually produced on this when I started in the project in 2014. We were already some years into that preliminary work, but only just beginning to start on really making things happen. And this whole book was produced. So if you're interested in the history, there's a whole book out there. You'll find it on websites and so on if you just put it in. This was before we changed the name to Shrewsbury Flaxmill Maltings. It had got itself called Ditherington Mill, though it was really just called by locals the Maltings in more recent times. So that's something to look for if you're really interested in the history. There's pretty much everything you would want to know there. So moving on now to the project itself a little bit more. Just here's a sort of architect's overview. Architects were Field and Clegg Bradley Studios throughout the many phases of the project. You can see the main mill here with its sawtooth roof. And just to illustrate in terms of where we're headed, really, in terms of the overall regeneration and use of the building, what we were going to be doing is then on the ground floor, making that into interpretation, museum space, open to the public, so people can come and see this first iron frame building in the world, whole extensive exhibition that's there now, and also quite an extensive cafe as well. Above that, because it's got a large amount of floor space, there are 4 floors for office use. One of those fully occupied now, the second about to be, and plans afoot, we hope, for the 3rd and 4th floors. And then at either end, in what were the engine houses, we have it works quite usefully in terms of design side of it, able to fit in all the services, plant room, loos and such like. And then the major circulation is in the kiln space, which was added, a great big kiln, one of the largest malting kilns in Europe at its time when built in 1897, which gave us a accommodation, as we'll see, to be able to put in the lift installation in particular, which was an essential part of finding a third use for this, the third use being this mixed use, leisure and work, education and so on, which we hope takes it forward. As our architects like to say, it had a first age as a flax mill, second age as a maltings, and now this third age, which has certainly seen some transformation alongside some very ingenious major repairs. I just introduced the main project team, because I think this audience in particular might be interested in that. So as far as the project partners, as Historic England ourselves as the owners of the building, we worked very closely, particularly to get the project off the ground and to pull together the funding and so on, with the Friends of the Flaxmill Maltings, a local voluntary group who provided a tremendous amount of community support through all those stages of the project, and Shropshire Council, who were immensely supportive too through the detail of the project. And very much on board with it, and still very much are. It's been very much a joint exercise with them in terms of a regeneration of this whole part of Shrewsbury, and a contribution to what they call the big town plan of looking forward to the whole future of the town, and the flax mill and this northeast corridor it sits on being an important part. As a budget for the main mill itself, 28 million, which largely depended on this successful lottery funded grant that we had of 20.7 million. So as with many major historic projects nowadays, it depends heavily on the lottery as the major source of funding. And this is the project team, our architects, and lead consultant throughout, leading all of the rest of the consultant team were Field and Clegg Bradley. Tim Greensmith was remarkably the lead architect on this from 2007 all the way through to 2024. So he's just moved on like myself. It's been a project that we've had a wonderful continuity of people across. The structural engineers were AKT2, with support at sort of sometimes at key points, also very much from our own Historic England structural engineering team. The quantity surveyors Gleeds, M&E was by E3, and a landscape, a smaller part of the overall project, LT Studios, and the main contractor was Croft Building and Conservation. We had quite a number of phases altogether, 3 major phases and some enabling works that we'll be talking about in particular, and then our own teams, including the engineers and myself as project manager, very much a sort of hands-on, leading from the top all the way through this project. So I want to move straight on then to talk about the iron frame and the problems that it faced. It being a great and innovative building, first iron frame building in the world, wonderful. Cast iron, as you'll know, being engineers, has its own particular problems. And to be honest, the cast iron frame for a multi-story building, I think this was something of a blind alley, really. They moved on fairly rapidly through the 19th century to wrought iron and then to steel, which have been much more successful. Cast iron has its limitations because, as you well know, it's very good in compression, but not very good in tension at all. And it sort of doesn't start to sort of bend and bow and sag a bit when it fails. It fails with brittle failure, suddenly snaps, and then you get cracks appearing like these ones here. And this is a particular defect that we had at a sort of column junction, which we found in this sort of location in about 2/3 of the places where it was opened up. So it's serious problems with that sort of brittle failure. But a wider problem with the cast iron scheme really was that it, because of this brittle failure characteristic of cast iron, what is now looked for in modern design codes in order to bring these upper floors into use again as part of the building regulations application and everything else that we needed to do. We needed the normal factor of safety that you would be expecting from cast iron because of this sort of slightly unknown and sudden brittle failure is a factor of safety in 5. And when all the engineering calculations were done on this, you found, as particularly on the columns, as you come down through the floors, that factor of safety came down to something around 2 in the worst cases at the ground floor. And it was a similar thing also to on the beams. The beams often had a similar sort of, and that was related to every floor rather than getting worse as the loads increased, obviously, as you go down. So there was a fundamental issue about sort of safe loading, which we had to address. A starting point for that in historic buildings and the Historic England advice over many years has always been to start by looking at, well, what loading does your actual building really need, rather than just taking the design codes, which are often worked out with sort of unrealistic maximums nowadays. And this is just a page from AKT's working through that, demonstrating the sort of crowd loading, the sort of heavy office loading with lots of sort of storage of cabinets, all that paperwork that nobody has anymore at all goes on a microchip. Meeting rooms with high loading, and then a sort of typical office which is now fairly lightly loaded and often rather more floor space per individual. So we started with this and said, right, well, actually, we're going to work around not sort of 5 kilonewton per meter squared sort of floor loading, but we will manage it on the basis of 2.5 kilonewtons. So that gave us a big head start to begin with. But we then still had some major issues in terms of how we were going to come up with a strategy for dealing with the iron frame problems. Essentially, one of the key things about this to sort of make is that what was realized early on, and there were sort of various investigations and trials done by the team in the earlier years. And we realized fairly quickly that what we didn't want to do was start interfering directly with the cast iron structure itself, as in trying to repair the cracks, as in trying to sort of strengthen it with resin applied to it or whatever. Anything that you do like that with a historic structure, it can be sort of seriously interventionist and often just sort of moves the problem on to the next piece of metal, really. So the approach in broad terms was then about sort of a very judicious and well-judged addition of new structure, new steelwork usually, to try and take the loads where it was absolutely essential. And what was devised eventually was to come up with this structure, which in particular is the loads of the columns coming down to the ground floor. So we put in an extra set of 6 columns only on the ground floor, trying to keep those to a minimum. And at the first floor level, as you see in red here on this screen here, a whole sort of grillage structure which spreads the load across. And we then needed just a central column on the first floor going up to support the second floor to do that. That obviously meant raising the first floor level significantly. We tried to keep that down as low as we possibly could, but we had to raise the first floor by about 2.25 mil or something like that, I think it was, which had quite an impact. But in looking at where to intervene on this building, we had a sort of clear view about the significance of different floors, and the first floor, which had already been compromised in some other ways, was actually the least significant of all of the floors, and in that sense we felt it was a reasonable thing to do. What we wanted to do was in particular to minimize the impact on the ground floor of the additional column structure, and that this scheme managed to do. So this is the whole grillage of steel going in. Looking down the spine of the building, there's a big sort of heavy double beams going either side of our central support, and those are supported by 6 very slender columns on the ground floor, trying to minimize that, and then out to the walls, and then that's raising the floor up above. And then we had to put in above that some columns just in the central part of it to support that. You can see here the jack brick arches and these tie rods. These of wrought iron. They could make these smaller sections of wrought iron back in 1797, where they weren't able to make larger components, which had to be cast at that stage. So that's the ground floor then, as completed before. It was all fitted out. It's now full of cafe and interpretation and so on. And we had a lot of angst and debate about this in terms of introducing additional columns. But this is what we ended up with, is these very slender 100 mil diameter steel circular hollow section concrete filled to get the absolute maximum loading out of those. And they're spaced really quite widely down at the centers of these alternate bays down the center here, and really quite a lightweight impact on our ground floor, which was going to be the one that the public would be seeing most of. On the upper floors, we were then able, having reinforced at the lower levels, we were able to reduce the intervention. We didn't need any more column supports, and the thing changed over to being really trying to increase the whole diaphragm action of each floor. So we were then putting in tie rods. These are the new tie rods, which there's 2 of those on every bay going across here. You can see them running across here, and that was introduced on every one of the upper floors. And then that was complemented by a fibre cement reinforced screed at the top of that. So you sort of ended up with a sandwich of a fibre cement reinforced screed, tie rods underneath. The tie rods could all be concealed. This is a big tie bar plate, which was recessed back behind the face and had to be all detailed around the beam bearings as well. So there's quite an intensive piece of building work goes into making all that fit together. So we were then getting this sort of whole diaphragm box action on these upper floors, which enabled us to spread the floor loading across, and in particular also then meant that we were able to address in this way the other major issue, apart from the issue to do with straightforward floor loadings and taking those loads, is to do also with disproportionate collapse. With this being a 5-story building, we were into needing to demonstrate to building control and to ourselves as well that if we lost one element in some extraordinary incident, that you weren't going to have the disproportionate collapse that a whole house of cards of this building coming down all in a collapsed heap. This is the tying up detail that was done fairly simply around those cracked bearings that we saw earlier on, just a stirrup, which then ties up either into the steels where those have been put in, or into this sort of spread diaphragm floor loading to take out that problem. So that's the iron frame side of things, and I want to move on to another side of things. First of all, one of the major design interventions we had to make was about the new windows. We decided in the Maltings era, most of the windows had all been blocked up, and we realised we were going to have to reopen the windows in order to secure a whole new use for the building in the Third Age. We had those bricked up openings fairly evident in the structure. And on one basis, you would think it might be quite straightforward to do that. It turned out to be a very complex piece of work. But just in design terms, just to pick out what I wanted to say, in particular this slide is about the decision that we took, the Maltings had installed then these smaller windows, timber windows, shutters really rather than windows. And rather than restore the whole elevation with that sort of back to a full row of all of those large size windows, we decided to keep both the original Flaxmill windows openings and the original window openings of the Maltings and give this sort of variegated look to it. That's the finished appearance there. So these are the new windows, new steel windows, all very high performance windows, and then timber windows in the malting spaces. You can see here the bricked up opening with its arch here of from the original opening there. But we decided we wanted to keep both phases of the building's history, and I think that's given it a historic and actually a visual interest in the finished appearance. But I wanted then to go to one of the most complex parts of the structural engineering program that we had to deal with, which is that this first iron frame building in the world turned out to have a concealed timber. It was really the Achilles heel of the whole design, that at each floor level, all the way across each floor level, all running a great length of the building above the windows, was actually buried within the thickness of the wall a timber beam, a timber plate or ring beam that went all the way through the building. And that had, predictably, as timber does in those situations, particularly where you've got damp processes like flax mill machinery and then malting, it had rotted out and created great voids within this highly stressed building. And this then had created major problems. And this is then just a sort of close up of one of the bits where the building was coming apart, and the reason why we'd had to put up that great scaffolding was actually a restraint scaffolding to buttress the external face of the building and stop it bursting apart, and actually to tie the whole building across internally together. Once we got to open up the building and see what was going on, this is what we found. This is the timber ring beam here coming across in the thickness of the wall. We're looking from the exterior. This is the end, rather nicely shaped end of the cast iron beam, which spans right across the building, the timber blocker piece. And then there's an iron rod that comes up here and was to connect, although it's all failed and rotted away, just great voids, connected into this timber ring beam. Most peculiar detail. Bit of a stupid one, really. They didn't do it by the time they were building the next phase of the iron frame buildings in 1810, thank goodness. And if it had just been the normal sort of thing of having a timber pad underneath the beam, we could have dealt with that fairly easily. But this was an absolute nightmare in terms of how we were going to deal with it. This is just a little further detail of that, and that's parts of this timber ring beam had these lap joints in it as it came out of the building. So our problem in dealing with this was that, in a sense, it was sort of fairly obvious what we needed to do. We needed to get all of that timber out and replace it with solid brickwork, or where it's a spanning element, we decided to place it with pre-stressed concrete lintels where we could do that. It was a hidden element. It had failed badly. We weren't interested in putting the historic timber back in because it had clearly been a design defect from day one, and we needed to sort it out. So we needed to remove the whole of that timber and replace it with sound material. The problem was that in order to get to it on the inside, our way to that was sort of blocked by the all the jack brick arches, and you would have had to take out a whole slice of those. And on the outside, we had this whole scaffolding system all pressed up against the building, all holding it together. And that gave us a sort of situation where, rather like a sort of underpinning the base of a wall, we could only take out very small sections at any one time of this support scaffolding. And you only had small little windows to work on. And it was then a case of working out a system of a buildability approach, really, of how we were going to get access to do this work. So this is the propping system that we needed to put in. So this was going to be a whole sort of exterior set of propping outside the line of the all of the scaffolding that we had, which is a sort of double depth scaffolding because of all the buttressing support. An inside line of props, and then regular needles across to support the brickwork as we were taking that out to do it. The issue being that to sort of thread that all through the existing scaffolding and so on was a bit of a nightmare. This had sort of defeated us all for quite some time, and we decided that the only way to do this was a sort of trial and error with a building company, a really well-skilled building company, Croft Building, to go at it and to basically carry out a whole full-scale trial repair contract on one bay and work out a system. And we tried one or two different ways of doing it and eventually worked out a way of coming at it. This is the exterior of the building that we were having to fight our way past. And these are the maybe props then that are then having to be thread through. This is the sort of existing scaffolding, other than that vertical big prop there, maybe propping system that's then threaded up through the building. Really quite small penetration, so we were able to thread through the crown of the vaults just with a small core drill and floor by floor go up there. On the outside, particularly on one side of the building, we had the further problem that we knew from our archaeological investigations and historic drawings, which we were pretty all on top of by now. We had a hole on this side, hole below ground, a lot of made ground over where the previous boiler houses were and the chimney and so on. So just to do the temporary propping system, we actually had to introduce this set of screwed piles. This is a great system because you can screw these things in and you can torque them up and get the check the load that you want and so on. Really quite a adaptable system for this kind of thing, but certainly add to the complexity expense overall rather than just propping from ground. And then the needling, which had to be quite a sort of major thing to hold up this whole building. We were really dealing with the sort of piers of building between the major window openings. So these were taking sort of major loading all the way down. There's one of the main spanning beam pads and so on. And this is the needling all around it. And we had to devise, working with the engineers and our own Historic England engineers, a lot of scratching heads about how this was to be done, and with the contractors working out a systematic approach. It ended up being about 12 steps of how we were going to open the windows, get all the timber out, only opening sort of small pockets at each one time, holding that temporary restraint system in place, building up the brick jambs of all these windows which had been destroyed really earlier on, and getting it all back safe and sound. Really was the only way to have done this. We did one whole bay, as you see here. It's a trial bay. Having worked out a system, we then went out to tender and for the main package, the other 20 odd bays each side, and then we're able to then have a really good quality control and cost. And in fact, this first phase of the building, which had been the highest risk part of the whole project, really came in about 1.8 million under budget, remarkably. Set us up very well for the rest of the project. As you can see here, it's really quite a major piece of engineering support, though, moving on each bay by bay as it was done. And at times, as you can see here, this is one of the piers here. That's clear space underneath that. So this needling and propping system was really having to do a serious amount of structural work during our work together. And then that's the finished thing there with the exterior back together again, the pattern of windows. And as with the best conservation work, and somewhat sad now when you sort of go around and people look at this and they can't see it. It's all invisible, all that wonderful skilled engineering repair. Nobody thinks you've been there at all, but then that's the hallmark maybe of the best conservation work. I wanted then just finally to move through some other aspects of the project. This is the that sawtooth roof. This was a major piece of re-roofing, obviously, with all the valley gutters and so on. Fairly straightforward Welsh slating laid on boards. We had to make this into a structural diaphragm, this whole thing. So it had a sort of, as you can see here, diagonal boarding, which was laid underneath the slates so that we got a sort of top lid to our structural diaphragm box out of this roof structure. But the particular thing of interest here was actually that when we dug into each of these valleys, we then found that we actually still had about 80–90% of the original cast iron valley gutters, which had been put in place in 1797. again, not a terribly clever detail in that they were just big long bits of cast iron bolted together with no allowance for movement. They'd been endlessly patched and bitumened and so on, and we really didn't expect to find anything when we went in there other than sort of felt and bitumen, but there they were underneath, and we were able to save nearly all of those. But rather nicely, we actually had to have some new ones made up. So we developed a bit of a partnership with the wonderful Bar and Grosvenor foundry, managed by a real character in the conservation world, Dominic Grosvenor, family firm. And we spent some time at the foundry there, which is an extraordinary thing, seeing the hot metal being poured out of a furnace. And then this is one of the big molds for one of those long pieces of guttering. And it really, to me, it gave you a huge respect for William Hazeldine and his original foundry there in Shrewsbury, making these much more sort of ornate and complex parts like long beams with all the castings and attachments and so on. And he must have had quite a failure rate, Dominic, even for all his skills. There was a couple of these that didn't come out. They came out with a few flaws in, and they had to go back into the furnace again and melt it down and try again. So there's our gutters, mainly the old ones refurbished, but a few new parts, about sort of 10% or so, about 5 or 6 lengths, I think it was in the end, of new parts, and a very much well-developed jointing detail with stainless steel neoprene gaskets. And in fact, actually, we put in another layer underneath that of a heavy-duty PVC sort of secondary layer underneath that. So it's a sort of very, if anything, over-engineered detail now, but at a sort of key vulnerable point in this multi-valley roof. So there's the roof going together with all the new Welsh slates. Great sight to see it getting its waterproof covering once again after so many years of leaking. So I wanted just to finish up then by just filling in. We've concentrated really mainly on the structural repair and the major building repair side of the project, but just to give you a flavour of the rest of it and the different uses of the parts of the building. This is the ground floor. We've got the cafe at one end of it, Lou's services, major plant room, and sorry, the kitchen and so on over here. Plant rooms on the floor above, and here we'll be seeing that in a minute. The kiln, which was a major addition of the 1897 Maltings phase, as we saw at that end, and the main interpretation space in the middle. There's the cafe as it's finished up. These are all polished concrete floors, new floor slabs, all insulated there, and working on through that. This is in the interpretation space, really quite innovative and quite extensive thing, which covers the whole, both the main mill, its iron frame, but all of the flax industry, the maltings. There are a lot of many stories to tell, and a whole lot of stories also about the workforce, the people. And rather nicely, from our point of view, there's a final part of it which tells the story of the project and the future of the building and this whole regeneration, a heritage-led regeneration, which is very much it's Historic England's flagship project, and it's been winning many awards, as you may have heard in just this last year, in particular, Civic Trust Award, Europa Nostra Award, quite a number of RIBA awards as well. And Historic England even won Client of the Year from the Architects Journal recently, which was quite a feather in our cap. Just touch on one or two other aspects. There's a whole one of our Historic England Technical Tuesday webinars about this, and the ground source heat pump, which powers most of the heating component of the building. About 2/3 of the heating supplies from this ground source heat pump, which has 10 boreholes which go down the incredible distance of over 180 meters, and this land just to the west of us, which we all own. This is the underfloor network of pipes underneath what's now the cafe and the interpretation space. This is the ground source heat pump plant room with the compressors, condensers, and so on, and hot water storage. Up on the first floor, that's been converted to office use, and this floor, having been compromised a bit. We've actually decided here to cut it up into cellular space, and we fitted that out completely. We wanted to get off to a flying start with those smaller units and be able to get occupation from day one, which is what we did. Those have been fully occupied from right at the beginning of the project. So we've got here loos at either end and this major lift installation in the kiln again. So that's the spec here. We went for quite a sort of, we wanted to set a high bar really in terms of what was to be done on the inside of this grade 1 listed flagship project for us, and to not end up with a sort of narrow little corridor space and feeling like you'd cut it all up. But this is the entrance end of it for coming from the lifts here. Generous size width corridor made for sort of shared workspace as well. Kitchen and work area here, big meeting room with glazings, and then more cellular offices still with glazing beyond them and so on. So that's been quite successful. There's the meeting room there, and one of the offices in there as well. So fairly modern fit out, as you can see, but very much making use of that historic environment space. People love working in this building. It is an extraordinary place to be in. And then up on the 3rd floor, which is the sort of most important of the floors, a great big, it was never subdivided, this space historically, unlike some of the lower floors. And is the one that you see the iconic photos of. We very much want to, in the future, retain that if we can as a single big open floor plate. We're still hunting for the right people to take that floor on. But that's that floor there, which is ready. All of the heating's fitted, all of the main sort of throughways for the wiring routes, lighting and so on are in place, all the services at both ends and so on. So we're looking for an occupant for that, if you know anyone. And then finally, just to talk about the kiln. This is the pyramid-shaped kiln, which had been the major place where all the barley was germinated. Barley was then turned into malt by the great furnaces. And this we decided to make into this major entrance atrium. This is people that use the word iconic maybe too much, but this is certainly a sort of quite an architectural icon, this space. It is an extraordinary, powerful place and a wonderful place to enter this structure from. Very different from the main mill and its iron frame here. We've got cast iron columns left from the 1897 building, though it had steel floors above, which were where the grain was all laid out. And then our architects have come up with really quite an innovative scheme for introducing a lift, grillage and so on, and then these walkways which take off at all different levels to service not just the main mill, but future phases of the building over this way, the 1810 grade 1 listed warehouse, and over the other way far behind there, the 1811 grade 1 listed cross mill, which are future phases. The design inspiration for those walkways is this Longdon-on-Tern aqueduct, the first iron aqueduct in the world, built by Thomas Telford just the year before. It has these big bolted up plates like this, and this was our Field and Clegg's inspiration for those walkways. And that's looking down into the kiln there. It is a wonderful space to experience. So I think that's the last slide there. There's the main mill frontage, and we hope the rest of the building's going to fill up soon and be a really beacon of what you can do with transforming historic building and sort of facing down those problems that it certainly had from its beginning, really, but with those behind us and often now receding into the background, we hope a bright future ahead. So thank you very much. We can open up then, Kim, if you want. Should I stop sharing and we can see each other, or should I keep things on if people want to see anything?
Keep it on for a second. I'll just ask everybody to unmute themselves, or give everybody the option to unmute themselves. Has that worked? Yeah, brilliant. Does anybody have any questions for Nick? Thanks, Nick. That was absolutely excellent, as usual.
I've got a question, Nick.
Yeah.
Thank you very much. I didn't know anything about this. It's fantastic. I didn't really understand. We had some technical problems, so I may have missed your explanation. I didn't understand what the window things were in sort of at the top end of on the columns. Yeah,
column heads.
Oh yes, sorry. Yes, I didn't. There's too many things to say about, so I actually didn't say anything about those. I should have done. So yes, those shapes. It's sort of like a forked head at the top of the column. Those are to take the line shaft, which then ran right down the length of the building from the turning steam engine at one end, and it powered a line shaft which went down the building, and then all of there were drive belts that then powered all the textile machinery, the spinning machinery, the heckling machinery, and all of that in the flax mill era. So what's intriguing about it, and I think it's just quite extraordinary, is not only this being the first iron frame building in the world, and that, Beige and Hazeltine managed to do that on such a large scale, but actually they designed in the whole of all of this machinery. So you've got this sort of forked arrangement, as you were noting there. There's one on the ground floor and there's one on the third floor, and the machinery was specifically, the whole building was designed to take machinery. There are quite a number of other designed in sort of fixtures and sort of threaded attachments for specific pieces of machinery. So, the whole thing as a factory was incredibly well thought through, and all of that had to be thought through, when you were there in the foundry, on the foundry floor, sand casting these elements, everything had to be designed in.
So they were taking steam. Forgive me, but I'm not an engineer.
So it was taking a line shaft, that's to say a whole rod, which was turning from the flywheel.
Okay.
So it was a turning rod, which was then driving wheels that went round, pulleys that then went off. So there was a whole sort of power transmission system running down the whole length of the mill. Yeah.
Thank you.
Yeah.
Do we have any more questions?
How is the overall stability of the building dealt with? It's quite long and thin.
Yes.
Do the floors do that? Or?
The floors do it, but there was actually part of the engineering design actually was to make sure that they were doing it rather more fully than they had been, because what had happened, particularly in the Maltings period, was that they cut some very large holes in the floor at various points to have sort of big chutes where they had water tanks or chutes for malt to go through and so on. So we've actually, part of the fire compartmentation structure, we had to fill in those holes again anyway, but it meant that we were able then to get the whole each floor to act as a sort of complete diaphragm. We also did quite a bit of making sure that that floor was then anchored all along the sides and ends as well, so that it was really strongly attached, which it hadn't necessarily been to the brick walls. The brick walls, interestingly, apart from this problem with the embedded timber within them, but one of the few structural problems we didn't have any problem with really was the foundations. They were very good, and so the brick walls themselves were pretty solid really. So once you've tied it together with the brick outer walls and then the floor plates, it did quite well.
Having the nibbles out of the words, but you can actually read it quite well, can't you?
Yes, I think so. Yeah, that was something we decided to do. It had been with putting the windows back. It was a sort of conscious decision to decide that we'll just go for that. And it's a bit like a sort of typewriter with a few bits that have worn off on it.
And can you hear me, Nick? It's Bill Addis here. First of all, well, I don't really have a question. For a start, I know a lot about the building already.
Good.
Even better. You have just delivered one of the best lectures I've ever heard on structural engineering in the last 40 years.
That's very kind of you.
Congratulations. That's really all I would like to say. I completely agree with your and other people's assessment. This is possibly the most significant building in the history of structural engineering. I write regularly about how the work around the 1790s and the early 1800s, and then into the work by Hodgkinson and Fairbairn, led to developing a completely new structural form in the form of what we now call the I-beam, and also
Yeah.
a beam that follows the bending moment and so on and so forth. So I couldn't agree more that it is absolutely amazing. I have a lot of contact in German-speaking countries, and in fact, I'm actually just today, for instance, I've been writing a chapter for a book about the origin of the frame building and where it led to, and so you'll be glad to know that this has pride of place at the beginning.
Wonderful.
But the extraordinary thing is, though, that outside Britain, cast iron really is a pretty foreign material.
Yes.
With the exception of columns. And they were using columns in Germany, for instance, in cast iron way up until the 1880s, 1890s.
Yes. Well, as columns, they performed quite well, I think, really, didn't they?
Yeah, absolutely, yeah. I mean, they're very good, but they have virtually no understanding of the important work that was done in developing the whole idea of an iron and then later a steel or a wrought iron and then a steel beam. So all I would say, Nick, is thank you so much. It was brilliant.
Thank you very much for that. I'll maybe just add to that to say, as you can probably appreciate, we all got terribly fascinated by the intricate details of this. And one of the things that we had during the project was we had an awful lot of opening up, and we could all sort of see the frame. And as people who work with historic buildings, you know, very privileged to see them when they're all being taken apart and so on. And we realized sort of as we were then putting the thing back together and so on, that we were actually going to cover up, you know, the sort of key heart of the structure. So one of the things, and I was particularly determined about this, that we decided to do in the exhibition area is we've actually left one of the sort of big holes into the structure around a key part where you can see all of that jointing, which would otherwise have been covered up, absolutely exposed, so that, you know, for those people who are interested in it, there it is, and you can come and see the real thing, not covered up, but actually, you know, really appreciate it. So yeah, they are extraordinarily intricate and extraordinary as well to me that alongside that technical innovation, they were also creating such a sort of elegant and you know, a thing of beauty. Really, it is remarkable.
Yes, I completely agree. I mean, to me, it is a work of total beauty. Brunelleschi's dome is really not very interesting compared to this building. No, I'm not serious. But the other thing, and I'd just like to say this for anyone, I'm sure you know this, but anyone who's listening, this was the first time that iron was used in a significant structural way as a new material, especially in bending. Which requires a great deal of care, as you have already explained very carefully. I think it's also very important for people to realize that they did not do this building by what a lot of people, in my view, pejoratively call trial and error. They did not build a column and see when it failed. They did not build a beam and see when it failed. They did very sensible calculations, both on the buckling strength of the columns, and although, as you observed, the cruciform shape is not the most efficient use of cast iron, ultimately, at the time, they couldn't cast a hollow
Indeed,
tube,
yeah, they were doing
iron.
what they could, yeah.
But they did very sensible calculation on the buckling strength of cast iron, and if you can't cast a hollow one, then a cruciform one is the next best thing.
Yeah.
And for the beams, they also used the most sensible available bending theory that was around, which had been around as a completely theoretical idea from let's say the sort of 1740s onwards. Because although they talked about using the bending theory to apply to stone or to timber, I mean, nobody needed to know that. They'd been building timber and stone buildings for about 5,000 years. That's right.
Yeah.
This was the first time that bending theory actually was used to deliver a building or deliver a building element that previously had never been built. And I can't stress the importance of the fact that they were using engineering theory in a very similar way to the way engineers use it today. And for that reason, it really is a gold star building. I mean, with beige, with strut, Hazeldine, as you've mentioned, again, without him, the whole thing would never have happened. But that trilogy of strut and beige and all those letters, I've never seen them. I would probably if I could read their writing, I would
Yes.
enjoy to read a lot more of it. But I've seen bits and bobs that various people have seen, and it's an absolutely brilliant story of amazingly high quality engineering in the modern sense of engineering design. It's not old-fashioned, trades of people working with well-known materials. This is absolutely the latest thing. Brilliant.
Great, thank you.
That's good stuff.
We've got a couple of questions in the chat, Nick.
All right, I'm not seeing the chat at the moment. I could stop sharing if we wanted to, but is that...
I can read it out to you. So Andy has asked, the longitudinal arches between the beams, very flat arches, must have produced a considerable force on the building. Was some longitudinal bracing introduced? My understanding was it wasn't.
Yeah, so I mean the key thing with those jack brick arches, which are quite a shallow span, is every time they've then got a wrought iron tie rod, so they have got individually for each of them. They have, and that was very much designed in. And interestingly, just picking up on Bill's point just there, that was a very intelligent use of the material. They couldn't make the larger components, as I said, out of wrought iron, but those tie rods, they knew they wanted those out of wrought iron, not cast, to take that tensile load. So they did largely take out, I think, the multiple longitudinal forces on each bay as they went down. They then actually had a sort of special arrangement of anchoring those final ties into the end walls, even right up at roof level. We discovered a whole sort of great big piece of timber which actually sort of slopes up and down on the top of the roof, which was sort of strapped in to the top of the iron frame. So they were careful to do that, and certainly that was not you often do see, don't you, at the end of a sort of long street of buildings or whatever, you'll see a gable end that's moving out or whatever. That's not a failure pattern that we had here, the sort of end cracking. Partly, I guess, because it's buttressed also by the independent engine houses, which were a part of the building originally, and then this south end here on the left-hand side of the view. That building was added they wanted a new engine. Bolton had gone out of date already, so that's 1810. So again, it sort of buttresses once again. So we didn't really ever have any problem with that longitudinal movement. I'm now seeing the chat. Right.
Do we have any more questions or thoughts?
Oh, there's Mark Watson here, who I saw, I think, there. Yeah, that's right. Hello, Mark. Yes, I think we've discussed this before about the bifurcated columns being secondary features. My view on that is that during the sort of process of doing what we've been able to do in terms of taking the building almost apart and getting it back together again, we've actually been able to show that those are integral with the original frame. I'm convinced of that now. We've been able to see that detail of how they fit in to the structure really up close, and there's no way that those forked frames have ever been taken out and put back in again. I think the evidence is quite firm on that. I know that as you've said in other buildings, that has been the case, but it certainly isn't in this case. I think there's fairly clear evidence on that now.
John Ruddy has a question. Microphone's not working. Having been in one or two other mills with the original machinery still in place, it really helps in interpreting what these buildings are about. Could there be any plans to recreate this in one or two bays on a floor? So
what's been done with that has actually been that, and in the ground floor of the main exhibition space, there's really quite an extensive amount of interpretation about that. We're not really able to recreate original machinery because again, the machinery sort of changed every 2 decades really, and the earliest machinery is actually there's not a huge amount of evidence of what exactly it looked like. But what we have done as part of the interpretation is, as far as the flax mill usage, we've actually, there's a small element where I was trying, probably rather inadequately, to explain about the line shaft and the belt drive and so on. There's a small part of that that's been set up as part of the interpretation, so that it sort of demonstrates that very clearly and visually how that was working. There are sort of quite extensive 3D visualizations and so on, which show that, and sort of moving models and so on as well. And then the other part, of course, is that we actually have two very different uses for the building. So there was also, apart from the original use with the machinery, there was then actually the maltings use, where it went to a very different phase. So again, for that, we've actually then got, within the exhibition space, there's a small section of maltings floor which has been set up. And in that case, unlike the flax mill use, which terminated in the 1880s and everything's gone, with the maltings, because it lasted till 1987, we have surviving photography, we have some surviving implements, so that's been set up with that, so that it can be demonstrated. So I think if you visit, as I hope some of you will, and go through the exhibition, you do get a very clear understanding. Obviously, you know, to have been able to set up part of a floor with the whole thing working might have been nice, but we've dedicated about 2/3 of the ground floor to this extensive exhibition. The first floors and above need to earn their keep as being viable office space, and so on.
Could I ask a question, please? It's Anthony Clark. It's the beams I'm particularly interested in. Are they 4 discrete beams over the 4 bays? Because where you have the line feeds, it looks like there's some continuity over the top of them. Or is it just the way in which...
Actually, if we just go back, I'll maybe just tell you what, I'll just move. I'll maybe just, I'll stop sharing at that point, maybe. Just say on that, so the way it works is that the beams are actually formed not in 4 parts, but in 2 parts. So they actually extend right over to the middle of the building, where there's a big flange plate. You saw that maybe being bolted together in that video. And the joints at the 2 outer columns, not the central column, it's bolted over. The 2 outer columns are actually, it's a continuous beam, and it has a spigot, and the other column, and the other one comes down into it. So it's it doesn't have sort of 4 parts, but 2 parts, those beams. And actually, that's in design terms, that's been a weak and a failure point, because it's where those beams are then passing over the columns, the side columns. They then have a weak point, and that's the way we've got this regular pattern of fracture cracking just there. Yeah.
So the fractures themselves, where it meets with the sort of curved bearing bit, and the fracture coming down, was that full depth or was it just partial depth?
Very rarely full depth, almost none. Certainly on the upper floors, almost none. There was just 1 or 2 which had been sort of historic cracks. One of which, the most sort of obvious and notable one, had actually been sort of patched up rather crudely and strap repaired. But there was about just maybe a couple or so which had cracked all the way through. Most of them had just gone, as you saw that photograph there, where it's maybe cracked through a half or 2/3, really. Yeah.
We're quite lucky with the connection detail there, weren't we? Because the plate projects out from the column bearing, which allowed them to still have some bearing, even though they were cracked through most of their depth.
It's just a bit strange, isn't it? With the cracking, you'd expect with the brittle material to go to full depth.
Exactly. Yeah, it's rather remarkable, really. Yeah.
Well, the reason I say this is that I worked for investigating Temple Mill, which was allied to this.
Yes, indeed.
We found the cracking of certain castings they had there was down to fatigue failure.
Right. The cracking, actually, just sort of going back on that. So the cracking in this case, the main theory that we have for the cracking is actually to do with, we think that the cracking happened very early on in the building's life, and that actually it was probably to do with the fact that it had these big, thick external load-bearing walls, which were then quite heavily loaded and settled a bit, probably within the first year or two, and so on, leaving the iron frame sort of more lightly loaded. And it being a cast iron frame, when it did that, you got some cracking in it, and those spigot lines were then the sort of weakest point really of where the cracking went. So we think that that was the sort of rationale for most of why the cracks are, rather than subsequent loading or anything else really, because there's this fairly regular pattern along those sidelines of that cracking. And maybe it's to do with that, you know, it was an early movement that then, you know, settled down, because you would have thought if it was going to crack, it would crack all the way through really.
Exactly.
Yeah, but it didn't. Yeah.
Thank you very much.
But there's some bending continuity there, isn't there? Which would put the bottom of the beam into compression.
Yes, I guess that's probably why. Again, you're testing my engineering knowledge on this. Really, maybe Kim's probably a better place to answer that. But yes, I guess you would then start to get a bit of sort of hogging over that column, and it goes into compression, which maybe helps it out from. It isn't just a sort of straight shear failure at that bearing point, is it?
No.
The engineers did quite a thorough assessment of the beams acting as continuous and as simply supported, to take into account and the cracking that had already occurred, and potential for cracking to occur in the future as well.
Did you have to provide any fire protection to the columns?
Yes, that was one of the rather annoying things about our fireproof building. Was that so it's built as fireproof, and one of the things that, you know, with building control and everything else was insisted upon was that actually we had to strip off all of the original paint and put on a intumescent paint system throughout. So that's part of the fireproofing for those upper floors and so on, which is what, you know, you often need to do with steel frames and so on now, isn't it? Again, one of the things, if you do go, what you must do is look at the column that's just next to the cafe counter, because there's one there that isn't particularly heavily loaded, and I was very determined that seeing those columns once they were stripped down and seeing the original finish of them and the various sort of, well, both the surface finish but also the floors within them and so on, is really quite instructive and a rare thing. And we saw the whole frame like that. There's now one column that you can see if you look for it next to the cafe, which we were able to leave without any paint finish on it, which is worth seeing if you've got an interest in that sort of thing.
Hi there, I can see someone with their hand up. Can I unmute you? Can you unmute?
Unmute.
Oh,
Okay.
There we go.
Hello, it's John. Marvelous.
Hello.
Welcome.
Yes, to revert to the piece about to the question about the continuity of the beams and the hogging over the intermediate supports. Bage clearly understood bending, and I don't think he had much of an idea about shear. He was obviously very good on compression. I mean, by this time, William Reynolds over at Ketley was calculating cast iron and did so at that aqueduct. But clearly Bage at least had an intuitive understanding of this. And bear in mind the circles he was moving in. I mean, this was Silicon Valley. You know, this is the West Midlands Enlightenment. He's dining out with the Darwins, and he's and all that circle. And so he had at least an intuitive idea that it wasn't a very good, that his first frame wasn't quite right. And indeed, in 1810 and 1811, with those next two buildings, he put in a much better detail, which didn't rely on a continuous beam.
Yes, he had that sort of shrink ring detail and separate things clasping around the column, didn't he, John? Which, as you say, and it's one of the nice things at the flax mill is that you can see, you know, within a decade, there are sort of already developments, not beige in this instance, is it? It's others picking up the same story, really, isn't it? But yeah, you see the fast developing technology, really.
Yeah.
Matthew Murray, I think.
Yes, yes, probably. We think we haven't got it sort of firmly attributed, but that's the general view that it probably was him. Yeah, yeah. Okay.
Is there anything else? The building is open to the public, isn't it? It's not open on Mondays, is that right?
Through the summer months, it's open, I think, except Mondays. It closes a little bit more through the winter months, but it's basically open certainly Wednesday through Sunday, I think, year round, sometimes on Mondays, Tuesdays through the school holidays as well. So it's open a lot. It's really worth going. If you are going, it's worth, if you're interested in seeing the whole site, which I'm sure you would be, make sure you book on a tour, because on a tour you get to go around, not just they don't take you through then the interpretation space and so on, where there's a huge amount to see in that exhibition, but you go around other parts of the site, and especially you go up, if you've got on a special tour, then you go up right high up in the Jubilee Tower, which is the big hoist tower that was added as part of the 1897 work. So it's well worth doing that.
Yeah, absolutely. It is a really impressive site. The first time that you see it is, I mean, well, every time you see it, it's such an impressive building, isn't it? Even the other buildings on the site that haven't been converted yet are equally as impressive, really, aren't they?
Yes, if you, from Iron Structures' point of view, the other great contrasting building, which is sometimes open with particular functions, exhibitions, and so on, is the Dye House. Which in its current guise built in the 1850s and has a completely different structure, now moved on to wrought iron and tensile structure, and very big, large spans, lightweight sort of thing, and makes a really interesting contrast with the cast iron sort of compressive structure in the main mill. So yeah, it's a really good varied site altogether.
Well, I'll say thank you very much again, Nick. Nick recently did another talk as Technical Tuesday on the J.W. Evans Silver Factory in Birmingham, which was also excellent, and I'm sure it's available on our technical conservation page on the Historic England website now, if anybody's interested to see that one as well. There's no meeting in December. It's a little bit close to Christmas, but our next meeting will be in January, and it will be the business meeting, and we'll send out an agenda a little bit closer to the time. But thanks, Nick, again. That was really excellent.
Really nice to share that with everyone. Thanks everyone for listening, and great to have such an interesting discussion with all sorts of interest raised. Thank you.